Let's review the economics of implementing a digital load controller onto a home or business. Today, we assembled an entry-level load controller for a total budget of around $350. So let's assume a total professional installation budget by a licensed contractor of $850, with the understanding that if you put the time in and do it yourself, obviously the project could be done more cheaply. Let's also assume that an entry-level commercial project might cost a little bit more than an entry-level residential project, maybe perhaps twice the size, and could be substantially scaled up from there. At the residential level, the best step for energy savings is to identify access to a time of use rate structure. So time of use rates will lower your electric rate for most of the week, but it will significantly increase your electric rate for a few peak hours of the day. My electric cooperative has a good time of day rate structure and even has a 6-month guarantee that any costs that might increase as a result of this rate structure would be refunded at the end of 6 months. But in the summer, between 3 p.m. and 6 p.m., Monday through Friday, I have a peak rate and then an off-peak rate for all other times. In the wintertime, the peak is only for a 2-hour period in the morning, again on weekdays only. So without time of day metering, I get a flat rate of 9 cents per kilowatt hour, and with time of day during peak periods, the electric rate quadruples to 36 cents per kilowatt hour. But during off-peak periods, the electric rate is cut down by half to 4.5 cents per kilowatt hour. So for 3 hours a day, 5 days a week, that's 9% of the year. It's called peak for a reason, so let's fudge the numbers a bit and assume that 10% of my energy use comes during this peak time. I'd call that a worst case scenario event when using a load controller. For example, time of rates could be a longer time frame than 2 or 3 hours. It could be an 8-hour rate. Or certain high energy activities such as intense electric cooking that must be done at 6 a.m. every single day and cannot be avoided otherwise. That could be very punitive for a shorter, more expensive peak time if it can't be avoided at any cost. But that's not the case for me. And if my peak load is a little higher than my average off-peak load, then by increasing my peak rate by 400% and then reducing the off-peak rate by 50% for the remaining 90% of the usage, that starting off out of the gate would decrease my electric rate by 5%. That's if my peak load is not that much greater than my off-peak load. And so right off the bat, using a electric load leveler, I think expecting a decrease in the electric bill under time of use rate structures is easily achievable. I'm more interested in what the savings would be if I substantially upticked my energy controllers, such as turning the thermostat off completely, turning off refrigeration entirely, and then testing to see how long the existing thermal mass in the home can coast through the time of day period while using the least amount of electricity possible. Filling a freezer or refrigerator up with thermal mass, such as bottles of water, could assist this effort, and there's even commercial products for filling your refrigerator with thermal mass, if you're so inclined. But by implementing the measures discussed in class, such as thermostat controls and shifting the dehumidifier, the electric savings for me could be 30% out of a maximum of 50%. The cost savings of 50% being if I used no peak energy and lowered my electric bill by 50% all other times. So that's the absolute top I could reduce my bill. And so I think I could do a healthy portion of that, 30%. So calculating the savings of time of use after the fact is a simple process. The electric bill still contains the total amount of electricity consumed. So it's easy to multiply by that amount by the old flat rate to determine what the electric bill would have been and then compare against the current bill. It's a bit harder to predict load shifting savings in advance, but there is a software which can help. Energy Toolbase is a commercial software which is essentially a glorified spreadsheet intended to calculate electric bill savings with the intended audience of solar or batteries. It's not anything that you can't model on your own, but it is a quick and professional way to graph out the energy use of a system and evaluate different rate structures for cost savings. For example, this building is revealed to have very spiky peak loads. If this were a commercial building being built not based on time of day, but on peak demand, those spiky peaks are a perfect time for an automated load leveling system to take non-critical loads offline. Imagine a hotel where for 15 minutes out of the day, the mini refrigerators would turn off. It would not impact the user experience of the room, but it could create substantial cost savings for the hotel owner. Even lithium ion batteries, which are expensive, can be cost effective in this sort of commercial load leveling. So all the more cheap digital controls are all the more cost effective, and they can work great in tandem. Now, I modeled my time of use rate within Energy Toolbase because it doesn't have my rural electric cooperatives time of use rate in their database, which is unusual. They're the market leader in electric rate modeling and structuring. A similar spreadsheet could be programmed in Excel or Google Sheets, but here the interface to get the spreadsheet set up is nice and easy. Now, I have interval data stored in my automation logger. So if I go a year, I can take that data out of my data logger, throw it into Energy Toolbase, and do even more exact bill analysis for even greater insight into time of use savings or battery sizing or solar storage. So data logging serves a real purpose for site planning and should be done well ahead of a project if the building is pre-existing. If I don't have access to this data, then essentially I need to guess how much my energy is peak versus off peak. So I can select, so that's what I do. I just take an assumption that, with my level system, keeping my peak use to be slightly above off peak is a 10% ratio instead of a 9% ratio. So now I can select between the flat rate and time of use rate to more accurately project my cost savings. So I'm modeling 3 different cases. The first is my current electric bill under my current flat electric rate. The second is the cost savings if I get into time of use peak and can manage my peak to have it be about equal to my off-peak use. And then lastly is how much I could save if I take my peak use and reduce it by another 50% and throw that into my off-peak section. So if my peak use is lower and significantly lower than my use in the off-peak time, how much could I save under that scenario, which I would say is the maximum realistic savings without solar or battery to completely eliminate your use during that time. So I found that by doing basic thermostat controls and energy automations, I could expect to save about $300 a year. And if I implemented even more aggressive digital controls, I could increase that to $500 a year saved through time of use metering. Both models assume some peak energy use, which could only be fully eliminated again with a battery. So that's kind of interesting. There are many people who want solar power but can't afford the tens of thousands of dollars in investment as well as the long term payback. A smaller investment in smart home energy controls can result in a 1 to 2 year payback while adding home automation value beyond the electricity controls themselves into other smart home functionality, such as multimedia. Cost savings of $25 to $40 a month on a $160 electric bill by doing nothing but shaping the home electricity use through automation is pretty impressive, I think. The payback on a $350 do-it-yourself project can be under a year. On a professionally installed project, that might be 2 to 3 year payback. On a commercial electric bill, the savings become even greater. A small commercial facility might be incurring a $10 per kilowatt demand charge on all power above 50 kW. Imagine a hotel owner has a series of 10 240-volt wall air conditioning units. Let's imagine that these are 5 kilowatt units each, most of which are running at full capacity during times of peak demand. Imagine if then we could reduce that peak demand by 4 air conditioning units simply by installing 10 controllers and then timing the units to power cycle in an organized manner. The demand savings from taking 4 units off of the peak load at 5 kilowatts each is a 20 kilowatt reduction in building demand. At $10 per kilowatt, the demand savings would be $20 per month. And so if each relay switch were installed for $200 each, the project could have a 10-month payback. And the material cost of these switches is, $90 when you buy one of them. And so this kind of price point is achievable within digital load controls. If the hotel owner wanted to be more aggressive in his savings, he could turn off all the air conditioners during peak times, resulting in a little more discomfort for the hotel guests, but perhaps an even greater windfall in cost savings. Another 50% increase in the cost savings would push the payback, almost down to 6 months. So in other words, digital load controls are the cheapest way to reduce a facility's electric bill, regardless of whether or not it's a residential customer with access to time of use metering or a commercial customer on a kilowatt demand charge. Now, originally, I thought a smart home should be full to the brim with data collectors. Now, however, smart homes aren't perfect, and it is possible to get carried away, particularly in new construction, filling up the home with smart devices and then failing to be able to bring them all in together in an elegant fashion. A smart home doesn't do anyone any good if it's not functional. So I found many devices are capable of sensing multiple inputs, such as this sensor, which can do motion, temperature, humidity, the amount of light in the room, vibration, and I don't know if I said, I guess I said temperature too. They sense a lot of things. It's called a multipurpose sensor. But most often you need a sensor for one specific purpose. Is there motion in this area of the house or not? So the other sensing portions of the devices, such as the amount of light in the room, are nice to have in terms of function, but on the other hand, they represent an unnecessary drain on the battery life of the product. So particularly I would not get too carried away with battery powered devices in a smart home. Smart smoke alarms are interesting because they can tell you exactly where the alert originated in the house. So if a fire starts in the kitchen, the alert tells you that that is where the fire started. And that can, result in better response times for the building inhabitants as well as for the fire or police department. Um, I was surprised when my dual fire alarm slash carbon monoxide smart sensor alerted me that my kitchen oven, under its cleaning cycle, was giving off some air quality alerts. This information is fun and it can be useful. We cleared out of the kitchen for that time frame, but it does come with a cost. As annoying as it is to change smoke alarm batteries, it is even more annoying to change those batteries more frequently and have to deal with bugs in the system, which might involve pairing and unpairing the smart devices to the smart hubs. You know, Getting up into the ceiling of vaulted ceilings to pair and unpair smoke alarms from the smart device is an annoying task. Furthermore, when a smoke alarm is directly paired to a security hub that has third-party monitoring services connected, it is possible for that alarm service to function as intended, and whenever an alarm is activated, it automatically call the fire department. And sometimes these smart hubs are not capable of differentiating between a carbon monoxide alarm and a smoke alarm, and so you can accidentally call the fire department because you're cleaning your kitchen oven because you have that third party service. So another solution would be to not pair the fire alarms to the security service, but have a audio listener to listen in on when the fire alarms are activated and use an active fire alarm signal to call emergency response teams. So pairing the smoke detectors to a security hub can result in more false alarms being phoned in to the emergency responders, but failing to pair the smoke alarms into the security hub means that they will only function as local alerts rather than have a more automated security function. Now, regardless, I recommend hardwiring these smart smoke detectors rather than leave them to battery power. Actual wall switches I was less impressed with. My recommendation would be to use full wall switch substitutes that replace the non-smart receptacle rather than adding on behind the switch controllers. Likewise, the touch controllers that I found were either quite expensive or somewhat finicky. The wall remote, for example, is like a magic wand for the home. It's capable of being programmed to do anything. If you have a smart TV that can be turned on and powered by the smart hub and turned to a station, you can program this wall remote to adjust all the lights, the curtains in your room, and really get the mood set for watching your favorite television station. But it doesn't serve as a good light switch on the wall. This is because it is a battery powered device, and the battery powered smart home devices need to be woken up before being used. So it doesn't really function as a good light switch because you can't just walk into the room and turn the lights on. You have to walk into the room, take the wall remote off of the wall, press the wake button on the back of it, put it back on the wall, and then you can use it as a light switch. It would be better at initiating a mode such as locking up the house for the night. It serves as a substitute to control the lights in the room, while sitting on a chair without the use of your cell phone. So, again, I don't know how useful that is as opposed to just getting everything set up on voice commands. A few months ago, a company called Span.io made a splash advertising itself as a smart electric service panel, and it's staffed up by a bunch of Tesla alums. They are not the only ones in this space. Lumen, Levitron, and even more mainstream brands like Schneider and GE have advertised their own kinds of smart electric service panels. Electric service panels are tricky because they're not really designed to be fed from multiple locations, such as a solar array or a generator and the grid concurrently. Home loads are tricky because they can be spiky as well. And so the electric grid helps average out all of our spiky loads. Together as a society, our power curve is steady and smooth. When we get down to an individual user, the individual devices clicking on and off can be quite spiky, as can solar production. The problem with backup solar batteries is that without managing your facility electric load, the output power that is required to power an entire home is actually quite large. One heating element inside an otherwise energy efficient air conditioner alone can represent a 10 kilowatt electric load. Now, a residential electric service panel is rated for 50 kilowatts, and so homes can see electric loads for very brief periods of time of 30 kilowatts or more. Just the control electronics necessary for a battery inverter to output 50 kilowatts of power can be $20,000 or more. In other words, the Tesla Powerwall at its $14,000 suggested installation price is going to be too small of a battery and too small of a battery inverter to power an entire house during an emergency. And we saw that this can be okay from an economics perspective to take advantage of time of use metering or demand management. But if the electric grid goes out and the building has a solar array or a Tesla Powerwall on it, and the building loses power because of a grid outage, the inhabitant is going to be aggravated unless they can use their solar array or battery to provide power during that blackout. So the industry is currently solving this problem by wiring up smaller critical load panels, which remain powered on their own output circuit from the battery inverter during grid outages. And this physically limits what the battery inverter can power, which often does not include air conditioning. But the best solution would be to install an automatic transfer switch between the home and the grid, and then manage the home's electrical load to operate within the parameters of the battery inverter such that the entire home can remain powered up during that outage, just at a lower energy mode. So some of these companies control and monitor every load on the electric service panel, and some just do a portion. And the end result is an expensive system that might also add value to other more expensive things already on site. But by building a site energy controller, either with expensive top shelf commercial product or more modest open source hardware, the same result is that the system can save the building money on their electric bill while being grid tied, and then also allow for more flexibility of on-site backup power for the whole building during an emergency while that building is being powered with an undersized generator, such as a gas generator or a solar battery. And that undersizing can result in substantial savings because otherwise you'd have to build a power system capable of delivering the entire building's worth of power and only using it during an emergency. Not that it's impossible to do so, but it's costly. And so even these expensive top shelf service panel monitors can play a role in reducing a site that's being prepared for off-grid operation. There is one Z-Wave accessory that might initially appear optional, but I strongly recommend getting it if you're implementing a Z-Wave network, and that's a range extender. Z-Wave does not have the range that it advertises, especially when you're transmitting data-rich signals. A non-critical sensor like a door or window sensor located outside in the yard on a mailbox to notify the home assistant when the mail has arrived, that might be able to transmit a Z-Wave signal over its full range while taking its time to make it from point A to point B over a long distance. Energy signals, which are updating every few seconds with a lot of information, put out more noise onto the Z-Wave network than a simple on-off sensor. And so although Z-Wave devices are intended as repeater stations, only the hardwired Z-Wave devices actually serve as repeater stations. And so all the battery-powered devices on Z-Wave network do not serve as repeater stations. They only do that when plugged in directly to the wall. So a dedicated Z-Wave repeater station reduces the stress of worrying about the quality of the Z-Wave network. And sometimes it becomes absolutely necessary if your controller and energy monitor are located on opposite sides of the house. So I strongly recommend using the range extender unless the hub is located directly within the utility room where the service panel monitor is located. If you like this program and want your own Raspberry Pi energy controller, why not buy one from me? I will pre-program it for you with a service panel monitor, 3 120-volt smart plugs, a Z-Wave thermostat, a Z-Wave USB stick, a range extender, and all the Raspberry Pi accessories you need to get started at a $499 price point. You won't find a better deal unless you do it yourself. So please allow 2 weeks for delivery.